Hello and welcome to the very last section of Unit 4. Yay! It's called Normality and Colligative Properties. I don't know if you've heard these terms before, but you will soon find out what they are. Before we start talking about normality, we need to define in chemistry what an equivalent is. When we use this term, we're usually referring to an acid or a base, and one equivalent of an acid would be equal to the amount of that acid that could furnish 1 mole of hydrogen ions. And then when we talk about one equivalent of a base, we're talking about the amount of the base that could supply 1 mole of hydroxide ions. Since bases produce hydroxide ions, acids donate protons. So that is the definition of an equivalent. The amount of the base that can provide a mole of either of hydroxide ions, or the amount of the acid that could provide a mole of hydrogen ions. Then, knowing what an equivalent is, we can talk about equivalent weight. When we talk about the equivalent weight of an acid or a base, we're specifically talking about the mass in grams of one equivalent of that acid or base. We're talking about grams, okay? So, knowing those definitions, we know that 1 mole of hydrochloric acid is equal to 1 equivalent of hydrochloric acid. And that is because the hydrochloric acid can provide, 1 mole of it can provide 1 mole of hydrogen ions, right? When hydrochloric acid dissociates into water, it produces 1 hydrogen ion and 1 chloride ion. So 1 mole of hydrochloric acid, that one's really easy, equals 1 equivalent of hydrochloric acid, because hydrochloric acid provides 1 hydrogen ion. Another thing to keep in mind when we're talking about this, the molar mass of hydrochloric acid is equal to the equivalent weight of hydrochloric acid. So when you look on the periodic table and you calculate the molar mass for hydrochloric acid, that will be equal to its equivalent weight. That will be the weight. The equivalent weight, remember, is the mass of that acid that can produce 1 mole of hydrogen ions. So let's look at a different acid besides a really simple one. Let's look at something like sulfuric acid. Sulfuric acid in its molecule has 2 hydrogens, right? So it can furnish 2 hydrogen ions per molecule. Just a little bit different. So 1 mole of sulfuric acid furnishes 2 moles of hydrogen ions. Every time we have 1 mole of this molecule, we get 2 moles of hydrogen ions, because this dissociates into the water. We get 2 hydrogen ions and a sulfate ion. So, if this is true, 1/2 of a mole is going to be equal to 1 mole of hydrogen ions, right? 1/2 of a mole of sulfuric acid will also equal 1 mole of hydrogen ions. I just took both sides of this equation and divided by 2. If 1/2 a mole of sulfuric acid is equal to 1 mole of hydrogen ions, that is 1 equivalent of the sulfuric acid, right? 1 mole of hydrogen ions is 1 equivalent of the sulfuric acid. So the equivalent weight is this 1 equivalent of sulfuric acid, or 1/2 a mole of sulfuric acid. In other words, it is 1/2 of the molar mass, because there are 2 hydrogens there. So when we take 1/2 of the molar mass of sulfuric acid, we get 49 grams. The equivalent weight of sulfuric acid is therefore 49 grams. So let's look at an example. Calculate the equivalent weight of phosphoric acid. Well, actually I didn't. I have a little typo here. Phosphoric acid produces 3 hydrogen ions. For each of the phosphoric acid molecules, we get 3 hydrogen ions dissociating into the water. So 1 mole of phosphoric acid furnishes 3 moles of hydrogen ions. Okay, Therefore, a third of a mole of phosphoric acid produces 1 mole of hydrogen ions. And we can find our equivalent weight of phosphoric acid by taking 1/3 of its molar mass. That gives us 32.7 grams. Now, you get to try using a base, sodium hydroxide. Instead of looking at the hydrogen ions that are being furnished by this molecule, you're going to look at the hydroxide ions. So pause the video and see if you can find out the equivalent weight of sodium hydroxide. Well, this was a very easy problem because sodium hydroxide only furnishes 1 hydroxide ion. Therefore, 1 mole of sodium hydroxide is equal to 1 equivalent of sodium hydroxide because sodium hydroxide only produces 1 hydroxide ion. And therefore, the molar mass is equal to the equivalent weight. So this is, in essence, its molar mass, 40.0 grams. That's also the equivalent weight for sodium hydroxide. Now, we're going to look. We needed to do this so that you could understand equivalence, so that you could calculate a new unit of measurement here called normality. Normality is not being normal. It's not being, it doesn't have anything to do with what you might think of normal in real life. In chemistry, it means something quite different. Let's look and see what it means. Normality in chemistry is represented by a capital N, and it's equal to the number of equivalents per 1 liter of solution. So you could think of it as equivalents per liter. That is what normality is, the definition of it. So a 1 normal solution contains 1 equivalent of solute per liter of solution. Obviously, if you rearrange this equation, you can get that equivalence will equal normality times the volume in liters, only if the volume is in liters. So you can rearrange that to find the equivalence also if you're asked to find the equivalence and you're given the normality. So it's a little bit different from molarity. Here's an example. A solution of sulfuric acid contains 86 grams of sulfuric acid per liter of solution. Calculate the normality of this solution. Well, let's write down our equation. We have it right here. Normality equals the number of equivalents per liter of solution. So in your mind, you should be asking, well, how many equivalents are there? How am I going to figure that out? And how many liters in my solution? So here I just rewrote the problem for us so we can look at it and wrote our equation down again. Let's start with the first question. How many equivalents are there in this problem? Let's start by looking at sulfuric acid itself. It can furnish 2 hydrogen ions per molecule, right? So 1 equivalent of sulfuric acid equals 1/2 a mole of sulfuric acid, okay? Which is what we were just doing a little bit ago. Therefore, we know that the equivalent weight is going to be 1/2 of its molar mass, which is 49.0 grams when we calculate that out. We know the equivalent weight, but that doesn't tell us the total number of equivalents in this solution, because in this solution, we have 86 grams of sulfuric acid. So we need to figure out the total number of equivalents by setting 86 grams of sulfuric acid and then multiplying by 1 equivalent being equal to 49.0 grams. That's our conversion factor. We have the 1 equivalent weight is 49.0 grams. These are equal to each other, so that can be our conversion factor. We put the grams on the bottom so that the grams of sulfuric acid cancel out, and 86 times 1 ends up giving us 1.8 equivalents of sulfuric acid. So now we know our equivalents. We'll be able to plug that into the equation right there. Now, how many liters? That's the next question. Well, if I have 86 grams of sulfuric acid per liter, I'm only talking about 1 liter. So my answer there is 1 liter. I can plug that into the equation right there. And what is the normality? Well, 1.8 divided by 1. Now that you know how to calculate equivalence and you know how to calculate equivalent weight and normality, we can talk a little bit about some colligative properties. What are colligative properties? I'm not going to tell you yet. I'll answer it at the very end. But let's talk a little bit about boiling. And let's just talk about boiling water, for example. You guys probably all know if we are at 1 atmosphere of pressure, which would be sea level actually, water will freeze at 0 degrees Celsius and it will boil at exactly 100 degrees Celsius. If we're down at our lovely little beach house at sea level and we're doing this experiment and we decide to dissolve some sodium chloride into our water, how will that affect the freezing point and the boiling point? Will they continue to freeze at exactly 0 degrees and will it continue to boil at exactly 100 degrees? Or does this solute in the water affect the freezing point and the boiling point? Yes, the answer is it indeed affects the freezing point and the boiling point. And I have a little mistake right here. It should be a negative sign. Here is how much it affects it. At 1.0 molar, a 1.0 molar sodium chloride solution, so we put enough salt into the water that we have a 1.0 molar sodium chloride solution, it will now freeze at about -1 degree Celsius, and it will boil at about 104 degrees Celsius. So that solute, in essence, those particles extended that liquid temperature range. In other words, it's called a freezing point depression. It lowered the freezing point to be even lower than it was, and a boiling point elevation. It raised the boiling point. Why did it do that? Well, let's look at how water boils. So when you watch water boil, I'm sure you've all noticed that little bubbles form in the water, and then they get larger and larger and eventually rise to the surface, right? So it starts out that there is a tiny little air bubble in the liquid, and then that bubble, the little teeny ones that you can't even see really, they will be able to expand as high energy water molecules, right? Water molecules that have a lot of energy, they're traveling fast, they have a lot of kinetic energy, they're able to enter into that bubble and produce enough internal pressure to push the water away and expand that bubble. Boiling then takes place when the vapor pressure of the water is equal to the atmospheric pressure. So remember, we always have atmospheric pressure pushing down on our water, right? It's pushing on it, and the vapor pressure has to overcome that atmospheric pressure in order to boil. And you probably already all know this. Atmospheric pressure alters the boiling point of water so that when we're at sea level, for example, water will boil at 100 degrees Celsius. When we go up in elevation, water will boil at a lower temperature, 93 degrees Celsius, because there isn't as much pressure. Atmospheric pressure is lower. There's less atmosphere pushing down on that pot of water. Therefore, those water molecules do not need to have as much energy in order to overcome atmospheric pressure. When we travel higher, the boiling point continues to drop. And then up here, we get, it drops even further to 79 degrees C. So why does solute affect boiling point? The liquid particles, the water right here, is easy. It easily shifts into the gas phase, whereas when we have solute particles that are dissolved in and amongst the water molecules, they are barriers to the water being able to escape, both by being in the solution as well as by being around those air bubbles that are present in the water itself. They prevent more water molecules from entering some of those little bubbles. Now, what about lowering the freezing point? Why would a solute lower the freezing point? You guys all realize this because in the winter, we have wonderful custodians who sprinkle ice on on the, or you sprinkle salt on the ice, not ice on the salt. Why do we do that? The salt, excuse me, it is the solute, and it dissolves into that very thin layer of water on the surface of the ice. It dilutes that water concentration, and fewer molecules are able to freeze, so it lowers the freezing point. Another example where you've seen this would be engine coolant. Ethylene glycol is a molecule that's added, and that helps to protect your engine both from overheating as well as from freezing. It extends that liquid stage longer so that your automobile will be able to go to a little bit higher temperature and be okay at a little bit lower temperature as well. So now we can define this interesting term, colligative properties. Colligative properties are properties of solutions that depend on the number of solute particles present. That's all. So the number of solute particles affects how much we see a freezing point depression or a boiling point elevation, and that boiling point elevation and freezing point depression, those are examples of colligative properties. So advanced ideas, what are other colligative properties? See if you can find out about that and explain those to me. Look at what molality is. That's another one that we haven't talked about. How does it compare with molarity? How might you calculate freezing point depression or boiling point elevation for different solutions? How would you figure that out? There's some nice little formulas out there. See if you can figure out how to use them. So I look forward to seeing you in class and seeing what you come up with.